What's up? Thanks for coming back. So what we're going to do right now is we're going to do a explanatory tutorial style video about vectorization with Python. So thanks for sticking with me if you watched the study sessions. You know, it was real nitty gritty and it was way longer than it needed to be, but we got through it and we learned so much, okay? So the point of this video is for me to come back around, bring it all together, and to do a concise, all-in-one explanation of what we learned about vectorization, specifically using the Python programming language and Numpy, the dependency Numpy, to handle this. Okay, so we're gonna start from the top and we're gonna take it all the way to the bottom. Let's do this. Okay, so starting from the top, what is vectorization? Vectorization is an approach to handling how we deal with calculations on the computer. So with machine learning, this is really important because normally when we do calculations on the CPU, it's done one calculation at a time, and then obviously the CPU is really fast. So with smaller data sets like arrays, data structures like arrays or scalar values, it happens just like that. You don't even have to wait to get the calculation completed. But when we start dealing with like really large data sets, things start to get really slow, especially when we deal with like really large vectors or matrices. So vectorization allows us to use the GPU hardware to execute code. And this is really important for doing linear algebra stuff, you know, matrix table multiplications and scaling and all that kind of stuff. And with larger data sets, the GPU is going to be a lot more performant. You'll notice that when you see infrastructure deployed for infrastructure like containers and services that are deployed to specifically handle machine learning applications or whatever, they're going to use GPUs because GPUs allow for what's called parallelism. And that parallelism just means that whenever you're doing something with an array or with matrices, all of the indexes, rows, and columns can have their calculations performed at the same time instead of procedurally one at a time. So what does that look like? Let's take a look at what a table looks like. This is like an example of data table for some features of a home that correlates to the price. And think about each of these as being columns and rows. Each of these columns is like an array, and these arrays together make a matrix, a two-dimensional matrix. So this is the thing that we're sort of thinking about when we're dealing with this vectorization in Python. I want to just quickly compare a vectorized approach versus a non-vectorized approach. So we'll start with the vectorized approach the non-vectorized approach first. So let's just say that we have two arrays, right? Array W and array X, which happen to be the vectors, is another way to call them, happen to be the vectors that are used in multiple linear regression. If we want to do the dot product, which is multiplying every index of array W by every index of array X, and we want to create a new array where each index is a multiple of the indexes from those two, that could be like this, where we do it manually, right? And then we include that into a new array of F. Or we could iterate over it and then treat it like a summation, like this formula here, a summation. Now with Numpy, it's really simple. There's actually a built-in method called dot that allows us to do this dot product operation. And not only is it less code to do it, since we don't have to write a loop or manually plug in all of the different indexes like this, but under the hood, this is actually using the GPU instead of the processor to do this calculation, which is different from the majority of the code that we've done up to this point. So this is kind of going to feed into the next section that we're going to have as a part of this little series, where we get into multiple linear regression. It's not necessarily important to know what this formula here means yet when you're looking at this stuff here, like some of these symbols, W2, X1, X2, X3. Don't worry about that right now. Just know that whenever we're dealing with two arrays, which are called vectors in this scenario, and we want to do things with those vectors, or if we want to have multi-dimensional arrays, which are called matrices, and we want to do things with those, the key thing that the key approach that we're going to use in handling how we deal with them is called vectorization. Okay? And Numpy makes it relatively easy to do that. Specifically, when we make a data structure using Numpy to hold the array, that's where we get access to the various methods and the ability to do different things like scaling and whatnot. If you try to do vector stuff like this here, you try to pass in a regular Python array, it's not going to work. You're going to get exceptions, because in order for the dot product to work, your array or your vector needs to have a shape assigned to its data structure, and that is not something that occurs with just regular vanilla Python. Okay, so let's go ahead and get into the Jupyter notebook that we started, which I think we spent a good, I want to say 4 or 5 hours working on this just over the course of those videos. Well, I don't even want to think about it. I know we spent a decent amount of time. Actually, I do want to know now. We spent a heck of time. Let me see. 2.5, 3.5, 4, 5, 6, 7. We spent 8 hours working. Child, please. Did we really spend 8 hours working on vector stuff? This was supposed to be a 1 hour lab. This was supposed to take 1 hour. See, if I don't leave this little course having gained some extra superpowers, because I straight up went Super Saiyan on this. Okay, I went Super Saiyan on all of this. Okay. Let's just calm down. That's ridiculous though. I definitely do be getting into it. This is what we do over here. Okay, we get serious business done. Okay, so let's look at vectorization, and let's not spend all the time in the world. Things you should know. The notes that I have for vectorization that you just saw here, available in the link below. It's the first little link. It's the PDF document. After this is done, I will also update the video description to have this Python Jupyter Notebook PDF in the link as well. So after this is done, whenever you're watching this, you should be able to go down below and see all of this below. And if you want to work on this yourself, all you have to do is just copy what I did here. Okay. Eventually I will get this in GitHub or wherever I decide to post these Jupyter Labs so that you can use them, or or clone them or whatever. But this is really meant to just be general notes. This is the kind of thing that you or I might create so that we could reference it in the future. That's why this is so dense. And this is based on a course which is listed down below in the description from Coursera, from Deeplearning and Stanford University. And I think that's about it. Yeah, so despite this being related to a course that I'm taking, I actually have done significantly more. Okay, I've taken their 1 hour thing and I've worked on it for 8 hours, and I expanded upon it and wanted to make something that you could take with you to know the ins and outs of what's really happening. Okay, we don't do shallow note taking. Our notes are cute and depthful. Okay, that's my big tangent, my soapbox. Now for real, let's go ahead and get into this. Okay, so we're gonna be doing this with Numpy. I don't know why I put time in here. I think I might have just been confused. Let me just run this again. I don't think anything broke. Yeah, I think we're good. I don't know why I have that in there. So we're using Numpy for this. Okay, so when we create an array in Numpy, when we create this np.array or anything that creates arrays like zeros, a range, or anything like that, what it's going to do is it's going to create an indexed list, indexed data structure that is organized, and it's just a set of indexes. Those indexes can be arrays. Those indexes can be scalars, which are just single values like ints or floats. Those indexes can be characters, pretty much anything, right? What's important when we're doing vectorization and operations for vectorization and machine learning stuff is that all of the things that are indexed in this data structure need to have the same typing. That's going to be critically important. There might be situations where you could get away with not having all the same data type, but as soon as you try to do scaling, or as soon as you try to do multiplication or anything like that, you're going to have an issue. And especially when you're thinking about numbers, even though 1.0 and 1 are the same thing, those are different types. So it's really just important to make sure that you are explicit about your types when it matters, or else NumPy might make some assumptions for you, or you might experience some unexpected type coercion. So make sure that all of the things that you're dealing with in your data set are of the same type when they exist in an array or in a matrix, potentially. I imagine that there might be cases where a matrix can hold data that is not the same type, but at least the columns need to have, at least the rows need to be of the same data type. And we'll get to what rows and columns are in just a second. Okay, so dimensionality is important. This is kind of it's not a complicated topic, but it can be a lot to wrap your head around if you're not used to talking about dimensionality with arrays or like tables and matrices. I guess the thing to know is that an array, a regular array that you see that's like a list of numbers or whatever, that is considered a one-dimensional array. A matrix is considered a two-dimensional array. And a matrix, and both a matrix and a vector is just an array, in NumPy speak at least. Both of those have what's called a shape. Now, the shape is going to be described by a tuple, which means in this case, two numbers, some number, comma, another number, is going to describe what the shape of that data structure is. That array, which can be called a vector, or that matrix, which can also be called a two-dimensional vector. So right here, the first thing we're looking at is vector creation. In this example here, we're just creating two vectors that have a bunch of zeros. And what this is showing you right here is that this first example here, this is just creating a array. An array, or a one-dimensional array, or it can also be called a vector. All those are the same thing. And this second example is doing the same thing, creating an array, one-dimensional vector, same thing. Now, you might notice here that in this first example, it's just a scalar being passed into numpy.zeros. In this other example, this is a tuple being passed into numpy.zeros. Now, NumPy is smart enough to know that regardless of how these are created, these are the same shape. Because when you see this comma and then nothing after it, in regards to describing a vector, this space here, this emptiness, what that means is that the elements that are included in this one-dimensional vector are scalars. They're scalars. They're not meant to be like additional arrays. They're not meant to add any more dimensionality. It's just going to be one-dimensional. So these are effectively the same way of doing something. The reason why you might do it one way versus the other could have to do with your approach to what you're building, which is not really pertinent for this situation. It's just enough to know that these two strategies are doing the same thing, okay? One thing to know, if you're looking at this particular example, is that when you do random sample here, random sample is just basically generating random numbers that are between 0.0 and 1.0. And that's how we're creating this vector right here. That's all that's doing. Okay. Yeah, so I think we can move on to the next little thing here. So this example right here, a range, what this is doing, what this method right here does, is this creates an array, a vector. I'm just going to call it a vector because that is going to be the more useful term from this point on. So just remember, when I say vector, I'm talking about a one-dimensional array. So this a range, what this does is this creates a vector that is the size of whatever integer you're passing into it. And this has to be an integer. So this is going to be a vector that has a size of 4. So it's going to index 4 things. So 0, 1, 2, 3. That's 4 size, okay? And for each of the indexes, it's going to have a scalar value assigned to the value of each index that has the same value as the number of that index. So the 0th index is going to have a value of 0. The first index is going to have a value of 1, so on and so forth. And you can see that here. So a range is going to make a vector of size 4 where each of the indexes has a value that is the same as the index. And in this case, we're passing in a float value, so that's what each of these are going to be. Same thing would happen if you did an integer, okay? So this next example, random.rand, this is pretty similar. It's still creating a, this is actually a matrix, but this is creating a two-dimensional vector, which is called a matrix. We're going to call it a two-dimensional vector till we get to matrices, by the way. So this is making a two-dimensional vector, and each of the, this is going to have 4 columns in it, basically. So four things within this two-dimensional vector, and each of those things is going to have 2 things within them. That's what this means when it says 4, 2, which also happens to be the shape. The shape. The shape of a vector or of a matrix is described by a tuple. So in this case, it's 4, 2. You can think of this as four things with 2 things in them. It's kind of the way that I think about it. 4 things with 2 things in them each. You can think about it as like you can think about this as being a vector that has 4 elements, and each element is an array or another vector of 2 elements. And this is what this looks like here. So you see 1, 2, 3, and 4. And each of these has 1, 2 in them. So 4 things with 2 things in them. That's really how I describe it to myself. I feel like it's much easier to think about it in terms of that. Let me just go ahead and get this much bigger for you. Okay, so that's what that does. There's some details in here that I'm not going to go over, but I think it's important if you do decide to read the PDF that I'll publish for this. Definitely look at some of these extra notes that I don't go over in the video, because there are some nuances here with what's happening as far as the Numpy dependency goes, but they're not important for this exact video. Okay, let's see, next thing here. I think we can skip this part. That's pretty much the same thing. So the next part here is indexing. This is a pretty standard thing that you can do when it comes to dealing with arrays and vectors and whatnot. All indexing means is it's like the way that you will be able to pull a value off of a list, off of an indexed list, an ordered list. So with vectors, you have indexes 0 all the way up to n. N is just like a number that can represent the full size of this data structure, right? So if you're like, let's say like your vector has 4 things in it, an index is a way to reference the index that corresponds to whatever thing you're trying to get. So the 0th index is 0, first index is 1, right? So in this case here, we're making a this is going to make a, similar to this right here, we're going to make a vector that has a size of 10, so 10 things in it. And each of those things within this is going to have a number, a scalar value associated with each index that is the same as the index, which is this. I know that's a mouthful, but just type it in your Python Jupyter notebook or something like that, and it'll make a lot more sense. Each of these numbers here is the number of the index, but it's also the value that is placed in that index. Okay, so in order to kind of explore this idea of indexing, what we did here is we're calling a specific index. So when we call the variable a with an index 2, that should give us the number 2, because that's what it is in this data structure. So the 0th index, the first index, and the second index. When we call a with the second index, that's what we get. That's so simple, but that's exactly how indexing works. Indexing is just referencing the elements of an array by its position. And you have to just remember that it's 0 index for Python. The R programming language is indexed from 1, and traditional math is indexed from 1. But in Python specifically, 0 index. And it's true for like Java and JavaScript and a bunch of other languages too. One cool thing is that when you do a negative number, let's say -1, that is another way to index, but this will index counting from the end. So if you do -1, it'll grab the last thing, which in this case is the number 9. So index of a, index -1 of a is 9. So this is like if you have a data structure that is of unknown size, but let's say you know that the 5th from the last index is going to be something you need, you don't have to like guess the full length of the index to get the 5th from last thing. You can just say -5, right? So just remember negatives count from the end. And that's nice because you don't have to like invert the shape of your, of your object or your data structure. You don't have to flip it around or anything weird. You can just do negative numbers. And then the last thing is if you have an index that you're calling or trying to pull a value from and it does not exist, then it will throw an exception. That exception will look like this. It'll say out of bounds. That's pretty straightforward. This will probably happen mostly if you forget that it's 0 indexed. So like if you do this and make an array, or I'm sorry, a vector that is of size 10, and you assume that you can get the 10th index, you have to remember the 10th index is actually the 11th thing, in that the 11th element. So just remember that you cannot go out of range or else you'll get an error. And that's what it says here in the comments. Okay, so indexing is a way to reference an element of an array or a vector, in this case, same thing, and you're doing it by its position, 0 indexed. Slicing, on the other hand, slicing is a way to produce a new array, and you pass in parameters that will describe a selection from an existing array. So slicing creates an array of indices using a set of values. The first one is the start. It means like if you have this array, for example here, this array of, let me make sure you can see it, sorry. Okay, there we go. So if you have this array here, 0 through 9, the start, which is the first number that we're going to use, the start is going to say where on this you begin your selection. And your selection is going to include whatever index you start from. So the next one is the stop. The stop is going to be like wherever you start to select from your start. So if you say we're going to start from the index 1 and we're going to stop at index 5, that means we're going to go here, right? And if you provide a number or a value for the stop, your slicing will not include the last thing, like whatever your stop number is. So if I say I'm going to index from 1, start at 1, and index to 5, then my selection is only going to be 1 through 4. I don't know why they decided to do it like that, but that's just an important thing to remember, is that your stop value is not included in your selection. Then the last thing we're going to pass in as a parameter for our slicing is the step. The step is just a way to describe the intervals you're counting for your selection. So if we do a step of 2, that means we're going to do every other one. So we're going to do our first, then we're going to skip 1, and then we're going to do our second, and then we're going to skip 1. If we do by 3, it'll be 1, skip, skip, 3, skip, skip, 6, so on and so forth. So the step is like, it's like the interval that we're counting before we select another one in our slice. So what does this look like? So for this first example here, or I'll just show you down here actually, I think this will be easier. So for our first selection here, our first slice, we're starting at 2, which is this, and we're going to our 7th index, which is here. And we're not going to include that one. We're going to go all the way to 7, and we're not going to include that one. So we're starting at index 2, going all the way to index 7. We're not going to include 7. And then our steps are 1. So we're going to include every step along the way. So 2 through 6. Okay, so the next example we have here is selecting from everything above a certain index, and there's a shorthand way to do that. Oh wait, no, I'm sorry. Let's look at the step first. So if we do the same thing that we did before, like this here, but we do a step of 2, then it's only going to include every other one, because it's like do 1, skip 1, do 1, skip 1, do 1, so 2, 4, 6. Okay, so in order to select something from an index and then get everything after that index, you can actually leave the parameters for stop empty, and then it'll automatically just know that you're trying to get everything beyond. So we're going to start from the 3rd index and get everything from there. So this will include here. It'll include the 3rd index and then everything else. And then the inverse is true for if we want to get everything from the indexes before. We do it like this. Oops, forgot to. We do it like this, right here. So we're saying that we don't care about the start. We want to look at the stop, or like the end. So our slice should end at the 3rd index, and it should get everything before that. So this. Now, if you want to get all the elements, basically create, I don't know why you would do this, but if you want to get all the elements and you want to do it in this approach, then you just pass in a colon here, and it'll basically give you the same array that you started out with. I don't know why you would do this, to be honest, but this is equivalent to just calling the vector, the array. So this is pretty straightforward. The big thing to know is that the start, stop, and step, if you leave the stop empty, then it'll get everything from wherever your start is. If you leave the start empty and only do the stop, then it'll do everything from the stop before, all the way up to like whatever the start of the vector is. And in any situation where you're defining a stop, whatever that index is that your stop is not going to be included in your slice. So if you want to do a slice where you're going from the 3rd index down below, you're going to want to make sure that you start that, or you stop that at 4, because it's not going to include 4 in that. It's just going to start, it's going to do like from 0 to 3 instead of to 4. It's a little bit confusing to wrap your head around. Definitely try this on your own and tinker around with it. Let me move my snap camera over here. I feel like I'm blocking the view. Okay. Anyways, back to this. Single vector operations. this is pretty straightforward here. Single vector operations basically means doing things that apply to your entire vector. So for example, we're gonna make a new vector here for 1, 2, 3. You can actually make all of the elements of this vector negative by just adding a minus sign. What this means is that the entire vector ends up having an inversion of whatever the value, like the positive negative values are for this. So positives become negatives, negatives become positives. That's what's happening here. You can do other things, like you can get the modulo of every index from your vector as well. So like we do modulo 2, and it'll return whether or not that number is divisible by 2 if there's a remainder. That's what modulo is going to do. It's going to tell you what the remainder is when you divide a number by some other number. So we can do that over the entire vector in just this amount of code, which is super cool. We don't have to iterate over them individually through a loop. We can square all of the elements as well. Another way to think about this, by the way, the squaring here, this is a form of scaling, which we'll get to in a second. But yes, you can do squaring over all of the elements as well. This is another thing that you can do with NumPy. You can actually take all of the elements and you can sum them up, or you can do an average. There's actually quite a list of things that you can do, calculations and whatnot, that involve taking all of the elements of some vector and doing something with it. The key thing to know is that you do not have to do that manually. And when you become familiar with all the different methods that are available, you can do things like averages, sums, means, all that kind of stuff pretty simply. So if you have like a bunch of numbers that you want to like do a calculation over, like a mean or average or whatever, just toss it into a vector and then you can do it like that. Okay, so vector element-wise operations. So with NumPy, most like arithmetic, logical comparison operations apply to a vector on an element by element basis. So here, what this is saying, this like little math notation is saying that assume you have a vector of A, and then you have an index from that, like the first or the 0th index, whatever index. And then you have some vector B and you have the same index as you had from A. And these all have to be the same size, by the way. You can create a new index for vector C of the same index of A and B. That is, the sum of those. And that's pretty straightforward. All you have to do, so in this example right here, we have two vectors that are the same length that both have different values in them. If you just simply add these vectors, it's going to give you a new vector that has the sum of each of those indexes. So 1 plus -1 is 0, 2 plus -2 is 0, 3 plus 3 is 6, and 4 plus 4 is 8. That's what this right here represents. One thing to know is that you cannot do vector operations when your vectors are different sizes. Well, you can't do it when they're different sizes. Let me just make sure one thing real quick, because I'm pretty sure this. Yeah. So you can't do like if your vector, let's say, is size 2, like this here, and you have another vector that's size 4, like this one here, you will not be able to add them together because that's like a meaningless gesture in linear algebra. And you will get an error. Your error will say something about the shapes of your vectors. So remember, this is the shape and this is the shape. This means that you have a vector with scalar values that is size 10. And this means you have a vector of scalar values that's size 2. And trying to add those together, it will not work. So similar to how we were looking at squaring all of the indexes in a vector, you can do other things here. These are generally called scaled operations. So you can multiply all the indexes, you can divide all the indexes, you can add some number to all the indexes, you can subtract some number from all the indexes. That is pretty straightforward. Okay, so getting a little deeper into this slightly more elusive topic is vector dot product. Vector dot product is going to be pretty important when we do multiple linear regression. There is a general formula for what is occurring when we're dealing with multiple linear regression with regards to how we manage the weight in relationship to the input. Assume that our weight and input are defined as A and B in these formulas, but it could be anything. It could be any letter, but let's just say A and B, right? So we have an array of features, and we have an array of weights, a vector for each of those. As far as how that fits into multiple linear regression, don't be so concerned with that right now. Just know that the essential operation that we have to do is taking two vectors that are the same size, like these two here, and we're going to take each index and we're going to multiply, we're going to get the product of each index together, and then we're going to get the summation of the products of each index. So this right here, so zero index product of A and B, the first index product of A and B, second index products of A and B, and we're going to take all of that for the entire range of these vectors, and we're going to get some value at the end. That's what vector dot product means. In the notes I was just showing you a second ago, the non-vectorized approach to doing this is really cumbersome. It would look like this, or it would look like this, right? If we were dealing with the weights and the inputs. The whole point of doing this in Numpy is that we can do this with just one simple method, which is here, np ... If you were to pull up this lab, when you go look at the PDF, I have a non-vectorized approach in here. But just remember that you don't have to do it that way. You can literally just take two vectors that are the same size and call np ... and it'll give you a new vector of C, for example, and that's going to have the same length as your original two input vectors. And it's going to have for each index the dot product for those indexes. So that's just like a quick way to do it, and it's also faster because if you don't do it using the numpy ... then it's going to be a lot slower, so much slower. And here's an example of the difference in time. So this is the time it takes for a vector. So let me back up just a little bit. What I did here for the example is I created two arrays, or two vectors. I keep calling them arrays. Created two vectors that are 10 million in length, A and B. And I did the dot product using the vectorized approach here. And I did the dot product using the looping approach here. The vectorized approach took 14 milliseconds. And the non-vectorized loop version of this took 2,866 milliseconds. I'm gonna run it here so you can actually see it live. I'm gonna run it here so you can see it live. Look at that, look at that, look at that, look at that, look at that. Bam, and it's finally done. Did you see how fast this first one ran? It's so fast, it doesn't even, like, it literally, vectorization literally does it in the blink of an eye. Bam, it was already done. 4 milliseconds. 3,000 milliseconds. We'll do it just one more time. Just watch. The first one that you're going to see is the vectorized, and the second one is the non-vectorized. Bigly different. Bam. Like you could have went, and made a cup of coffee, made some scrambled eggs, taken the trash out, brushed your kitten. You could have probably taken a nap, watched the episode of Game of Thrones. You could have done all of that in the amount of time it would take to do this non-vectorized approach. Okay, so yeah. The reason why this difference exists because of parallelism, what I said at the beginning of this video, Numpy makes use of data parallelism by using the underlying GPU hardware. Now, in comparison, what is happening with Python without using this GPU hardware is called single instruction pipelines, and we're doing like the opposite. We're taking single instructions and we're actually treating them as multiple data pipelines. So that's the difference. Normally it's a single instruction pipeline where you do things like one at a time, like lined up in some type of queue, and then they get done, where the GPU is allowing us to take a single instruction and treat single set of instructions and treat it as multiple data pipelines. So happening in parallel. Yeah, so multiple operations get to be completed, and that makes things significantly faster. So I have some notes in here that are about univariate linear regression and multiple linear regression. This is not pertinent for this specific video, but I want you to feel comfortable reading this part and understanding it, because this is going to help in the very next video study session / explanations that I do. But this is important because this ties into the matrices. Matrices are going to be the major thing that we're using with multiple linear regression. So I'm going to skip this part for now, but just know that it's worth reading and coming back to when you get a chance. So matrices are two-dimensional vectors. The way to think about it is like a table where all of the rows and all of the columns have different references. When we're talking about multiple linear regression, all these columns, for example, columns of X might be considered different features, right? And all of the rows within each column represent a different value that is included in that feature, a different index. There's two primary ways that this is communicated in math notation. By the way, there's a link down below in the description that has some, like a cheat sheet, PDF to math notation stuff for machine learning and deep learning. Check it out. But there's two primary ways that you're going to see this communicated in math notation. One way is the pattern of having the super and the subscript, where I is the row and J is the column. So I is the row horizontal and J is the column. And the reason why this is important is because this notation allows us to define exactly what value in a matrix that we're talking about. So what does this look like when we're talking about organizing this in a more of a pseudocode style? So each of these elements of the vector contains two elements, right? So for example, what we're looking at right here where my mouse is, this has a size of 4.2. The top number here represents the element within the contained vector. And there's 4 contained vectors. There's 4 contained arrays within this super vector, or whatever you want to call that. So the bottom number, it just represents the column. This is really confusing, by the way, if you are not like having gained an intuitive approach to this. Just remember, you don't need to internalize this math notation part unless you're interested in interpreting math as code, which you will be at some point. But for now, just remember that there's 2 ways to represent this. The top number and the bottom number represent the row and the column. Row is horizontal, column is vertical. Columns are like individual features. Rows are indexes within those features. So the top number is the row, which is the index, and the bottom number is the column, which is which array within this vector are we targeting. And then basically the other way to communicate this is by having both the subscript. I don't like this approach. That's also what's happening in this little image down below. This can be a little bit confusing because if you're not familiar or if you don't know that that's what you're looking at, you could easily think that you're looking at 10 or 12, 21, 22, and it's not what you're looking at, okay? So I would say if you're going to do it that way, use parentheses, but generally just don't do it that way. It'd be better to use the super subscript approach here, I would think. Either way you do it, make sure that if you're going to do like a latex notation for like some document or whatever that you're creating, at least put a key. That way people know what you're communicating, because it can be really confusing, okay? So these two notations are describing the same thing. The top number here, I over j, the top number is the row, the bottom number is the column. Rows are horizontal, columns are vertical. And this is a way to position some value within a matrix. Matrix is a two-dimensional vector. It's a vector of vectors. A vector, this whole thing is a vector. Oops, a vector. And then each element within this vector is also a vector. This is really recursive language, by the way, so it is very difficult to talk about. I kind of struggle talking about it, but the talking about it also helps you to figure out what you do and do not understand. So it's still helpful, even though it's awkward. Okay, so yes, so what I was saying before is that vectors for NumPy and matrices for NumPy both have shapes. Here, what this is just playing around with some methods that are available whenever you have a data structure that is of array type from NumPy. You get a bunch of different methods. So if you want to know, or you want to be able to provide a value for what's going on, you can call .shape. .shape is going to give you the shape in the form of a tuple. So for this one here, this is 4 by 2. So this is a vector. This is a vector of vectors, which means it's a two-dimensional vector, also called a matrix. The matrix. This is a matrix that has a size of 4, and each vector within this matrix has a size of 2. So 4, 2 is what we're looking at here. 4, 2. When we call .shape, it's going to give us the shape of this matrix. When we call ndim, it's going to tell us the size of each element within the matrix, each vector within the matrix, which is the second number here. And then if you want to know how many columns are in this matrix, it is going to be .shape 0. That's going to give you the number of columns within your matrix. There might be situations where each of these is important. The reason why I did this here was just to show you that you can get these values without having to destructure this tuple. You can get them just separately with their own methods. You can get the number of elements, the number of total elements in your matrix, regardless of how they're separated into vectors, or rows, or whatever. You can get the entire quantity of elements by just calling .size here. Whoops. .size. I think you can also get the data types. Let me wait to do that. I'm gonna wait to do that. This transposition, what this means here is for the size. So if you think about the size of each of these vectors that are contained in our matrix, they represent two values. So let's say like an X and a Y, or index 0 and index 1. If we wanted to make the number, if we wanted to make a new matrix, let's say we want to make a new matrix where the size of that matrix is the number of elements within the vector, where the vectors in that new matrix are groups of all of the elements from the original matrix's vectors grouped together. So let's say like we want to have 1 and 2 and 3 and 4, which are all the 0th index of each of these vectors. We want to have all those grouped together, and then we want to have a group that is 2 and then 3, and then 4, and then 5, and we'll have all of those in its own vector. Like to split this up, basically, we can call transposition. I think a simple way to think about transposition is that we're creating a new vector that is a new matrix that has a size, dimensionality of the number of elements within the vectors. That's like a really, really weird, obscure thing to do. I don't know what situation you want to do it in, but I think if you just look at this here, the pattern makes sense. This first group is this 0th index, the first group here, is literally the zero index of each of these vectors, all sort of like put into the same vector. And then this first index, the second group here, is literally all of the first indexes of each of these vectors put into a group together. Does that make sense? I hope that does. I feel like I didn't make sense when I explained that. So yeah, that's a thing. I don't know. I think where this might make sense is if you have like you know how in univariate regression you have x, y values like a target and an output. Let's say you were to get some data and it's like structured as a set of arrays where the first it's structured in a way where like things are grouped, like x, y's are vectors, and you want to separate those out into two separate vectors instead of having everything paired together. Like let's say you had like x1, x2, x1, y1, x2, y2, and you wanted to separate all your x's and y's into their own vector. You could use this transposition to do that. If you did not follow anything I just said in the past 5 minutes, don't worry, I also did not. So let's just go ahead and move on. Okay, so what else can we do with NumPy arrays? The basic structure of NumPy array is n dimensions containing elements that are all the same type. We talked about that earlier. The way you can determine what the type of your array is, or all the elements of your array is by doing dtype, and it'll give you some output. An example output would be, I think I have an example up here. Like this right here. This is like the example of the kind of type that you'll get. So float 64 and 64, you know, character, string, like whatever. So just remember that if you're getting issues with your vectors and like matrices and stuff, it might have to do with data types. So always check that. This is the shape that we just talked about. Oops, this is the shape we just talked about here. And this shape here is, the first one's going to be the number of columns, the second one's going to be the number of rows. When you see M and you see N, these are usually referencing to the size rather than a specific index. So M means like the size of the number of rows, and N means the number of blah blah blah. M means the number of columns, and N means the number of rows. This is not necessarily indicating a position, but rather the number, like the size or the shape. So M and N. You'll see N as the value that we use to set the range for doing univariate linear regression, and you'll see M used to describe how many features, the number of features or columns that we do in multiple linear regression. Matrices are used to hold the training data for multiple linear regression, by the way. So matrix creation is similar to vector creation, except we're defining it with a tuple explicitly. And this tuple, even if we do one column, a vector and a matrix are still considered separate data structures. So a matrix with one column will look like this right here. Oops, will look like this. But just remember that this is not a vector. This is not an array. You see how it's enclosed in two brackets? All this right here means is that This is size 1, 5. So there's 1 column and 5 rows. And this is a little tricky because we're seeing this like spread out horizontally. Just imagine in your head that this is actually presented vertically, like with each of the zeros vertically arranged. That's probably a better way to think about this. First number in the shape is the number of columns, and the second number is the number of rows. If you were to see an array instead would look like, I'll just type it out here. An array would look like this. Oops, I gotta do. Oh. I can't call shape, so I can only do, because arrays don't have shape. Actually, no, I can do this with Numpy. Yeah, there we go. So if you see like here, this first one is a vector, this A shape. This is a vector with size 1, 5. So 1 column, 5 rows. That is not the same thing as an array that has 5 items in it. Let me add one more here. So this here and this here are not the same. That was confusing for me, and I know that it'll be tricky for someone else who's not, used to this. Where it will matter is if you were to try to do like matrix to matrix operations and you were accidentally using a vector, and if you were using a vector and then some matrix that had 1 column in it, that's the same size as your vector. Like stuff between those two will give you all sorts of weird errors, and I'm going to show you those in just a minute. But just remember that these are not equivalent. What else? Yeah, here are just some more examples of sizes. So 2 columns, and each column has 1 row, which basically is this. This is like a vector that has 2 vectors in it. And each of these contained vectors has 1 element. So it's a matrix that has 2 vectors in it. And these vectors are 1 dimension, 2, 1. And then this here is just another example, pretty simple. Like I was saying before, the way that we talk about a matrix is with the tuple, column, and then row, and it's going to look like this here. And then an array is just going to have 1 set of brackets. So just like we did scaling with vectors, we can also do scaling with matrix as well. I'm not going to walk you through all of this line by line. I think it's better to just look at the output here. So you can scale a matrix by any shape with an array. As long as that array, actually the size of the array doesn't really matter, because what will happen is it'll take the matrix and it'll take every element and it's going to scale it by whatever that array is. And you can also do it with the scalar as well. What's the reason why this works is that scaling just means that you're broadcasting over all the elements of your matrix and you're performing some operation on them that is in relationship to 1 value. So when we have like a array of size 1, like in this case 0, then we're taking the 0 and we're doing something with it. We're broadcasting that thing over all of the elements of a matrix. That's pretty straightforward. And then the output is going to be the same size as whatever your matrix is, even if you're doing it with an array or with a scalar. Now, where things get a little tricky but still work is you can actually do this scaling even if the columns are different sizes. So meaning, like, let's say you have a matrix and your matrix has more than one row, like 2 rows. So you're doing 2 columns and 2 rows. You can still broadcast a array of a size 1 or a scalar over this. The number of columns and the number of rows that exist in your matrix do not impact or prevent you from doing the scaling. Scaling can still occur. So where things get tricky is when you start trying to do dot product. Dot product requires you to have the same shape between the 2 things you're doing dot product against. Because if you remember, the way dot product works is it's assuming that both matrices or even both vectors, it's assuming that each of those have the same number of indexes, and it's assuming that each of them have the same number of rows and columns. That's the only way it'll work. So if you have the same number of columns and different rows, you're going to get this error, and the error will say that there's this misalignment with regards to the shape. If you try to do different columns, but a different number of columns with the same number of rows, you're gonna get the same error. I mean, different numbers here, but similar error. And if both the columns and the rows are different, you're also gonna get an error. So just remember that when you do matrix to matrix dot product, the number of columns and the number of rows have to be the same for both of the things you're passing into it. But if you're doing scaling, then you can have 2 different shapes as long as whatever you're scaling with is one-dimensional or a scalar. Let's see. What this is saying here, this is pretty simple. This is just creating a matrix, and it's just saying that when you're creating it, you can actually separate things into different lines. This is a much better way to, a little bit better way to think about the shape of your matrix. Only thing that's a little bit misleading is that it makes it seem like these indexes are rows, and these indexes, let me back it up. It makes it seem like each of these vectors that are contained within our matrix are rows, and that is not true. Each of the vectors that are contained within your matrix are actually columns, and each of the elements that are within these vectors are rows. But if it's visually helpful, just for the sake of organizing data to do it this way, it's fine. Just remember that this is like actually a little backwards from what you would see if you were to talk about this in terms of like matrices and stuff in math. But the key thing here is that you can actually have these on different lines, and that's not going to make a difference in terms of your compiling and stuff like that. That's a pretty general programming thing, but you know, the purpose of this document is just to kind of experiment and play around. So now you know. Let's see. Okay, next thing here, operations. This is the last 2 things here. So similar to how we were doing indexing before with vectors, you can do indexing with matrices. Remember that when we're talking about positioning something within a matrix, it's I, j. It is, wait, I think I got that backwards. Sorry, just 1 second. Okay, yeah, I got that correct. So the I represents the row, and the J represents the column. So if we were to think about this matrix right here, and let's say we have a matrix here that has a size of 3, and within it, each of these vectors has a size of 2. Well, we can actually pinpoint some specific location by using what's essentially a coordinate system. The way that we do this with matrices is we call what's called reshape. So in comparison, if we had like some array, and that array was like this, we could call the index of some array like that, right? And this would be the first index, which would be number 2. That doesn't work with NumPy. With NumPy, we have to use this method called reshape. Reshape, the first argument that we pass into reshape is the number of columns, and the second argument is the wait, I'm getting confused here. Yeah, so what reshape is going to do here, it does 2 things. Now, reshape just on its own is going to take a vector and it's going to organize it into a matrix. And you can define how it'll split that vector up into a matrix. So -1 in this case means that, well, okay, the first value here is the rows, how many rows we want, and then the second one's how many columns we want. When you pass in a -1, that means that it is unknown or it's undefined, and you're going to let the program determine that for you. And the second one is the number of columns. And in this case, we want to have two of those. So reshape is going to do that for us. It's going to allow us to convert a vector into a matrix. Now, if we want to actually select, some specific value from our matrix, it's similar to what we do when we're selecting an index from a vector, like with the square brackets, except we pass into it a tuple, like 2 numbers, and those 2 numbers are essentially the coordinates, like this right here. So, for example, if we want to select the third or the second index from this matrix, which is the second index means like the second indexed column, which is going to be the third thing. So 0, 1, 2, right? So the second index from our matrix, and we want to select the 0th index from that vector, which is going to be the number 4. So just remember that when we're selecting a value from a matrix, it's the square brackets on the matrix, and then it's going to be a tuple, which represents the column and row. And actually, I think I have it backwards here. This should be J, comma I. I was like a little bit confused there, but good thing I picked that up. So this order is a little bit backwards, and I think my Roomba's going off, which means I have to get done with this pretty soon. Okay, so accessing a row in a vector. Okay, so we can do 2 things with this square brackets here. We can access a specific element within our matrix, in which case we need to have a tuple, 2 values. Oh, my Roomba. And then the second thing that we can do is we can access an entire column within our matrix, and that entire column in this example would be like this one here, 4, 5, which is the second index within our matrix. So we're gonna call this here, which is this here. So HA reshape 2. That's gonna give us this 4, 5. Give me just 1 second. I'm gonna go grab my Roomba because it is distracting me. Sorry, just 1 second. Ooh, the ghetto. Okay, that means it's 6 o'clock. So, so, so yes, I'm sorry. That was a moment of chaos for me. Key things to take away from this little code block here, and everything's in the notes here, is that you can actually access elements and you can access columns. Elements require you to have the coordinates essentially that represent the column and the row, and to just get a column, all you need is to have a just a single value here, a single scalar value. And this is basically the same thing you do when you're selecting an index from a vector. You're essentially treating a column as an index on a matrix, as if the matrix was itself just a vector. So I think there was something I need to fix here. I think I just had this backwards. Okay. And so just remember that when we're doing reshape here, the only reason why this is in here is just to show you that you can convert a array, just a vector, into a matrix. And -1 means undefined, and 2 here means that you want to have 2 rows in every column that is created of whatever number of columns is needed in order for the data to fit. By the way, this reshape only works if the dimensions you're defining here allow for it. So so your data has to be evenly distributable with whatever tuple you're passing into it. -1 means that you're going to allow the compiler or whatever the code to determine either one of these. You cannot have 2 undefined ones though, like doing -1, -1 will not work. You have to define explicitly either one of these 2. That's something that I noticed when I was playing around with it. And then I also confirmed that with the documentation as well. So let me just get rid of this extra space. That looks weird. Okay, I think we can move on to the last one here. So last one here is slicing. Slicing for a matrix is pretty similar to slicing for a vector. Remember, slicing creates an array of indices using a set of 3 values, a start, a stop, and a step. Your start, whatever that index is going to be, it will be included in your new array, and your stop number, that index will not be included in your new array. And the step just means the number of counting, the counting number that determines like what gets included. So if you do 2, it means every other one. If you do 3, a step of 3, that means every third one. Step of 4, every fourth one, so forth and so on. So the number of columns. If we do this reshape here, this is like what we were doing before. We're going to take a vector that has 20, a size of 20, and we're going to reshape it so that we have some number of columns where each column has 10, a size of 10. And in this case, it's just going to be 2 columns with 10 rows, which is this right here. Another way to think about this formula, if you're confused about how this reshape works, is you take the range divided by the rows, and that tells you how many columns. And then you could also do the range divided by columns to how many rows. So you can only leave one of these undefined. But this is like the formula that describes what's happening here. So if you want to get like only 5 consecutive elements from our little matrix here, then the way you can do that, let's say you want to do it only for the first vector within our matrix. Well, the first thing is that you have 2 parameters, or two things that you're providing for this slice. The first thing here is the index for the vector you want to select from, which in this case is going to be the 0th, which is this one right here. And then after you pick the vector you want to work with, then you can just do this regular slicing thing that we did before, where you have a start, stop, and step. And that is the same as what we did before. So we don't have to talk about this part here. It's just the same. The key thing to know is that you have two things here because you're dealing with something that has two dimensions. So let's say you want to do a slice, but you want your slice to happen against all of the elements, or all of the vectors rather, within your matrix. In that case, you do this shorthand here. So remember, when you pass in a number here, this is just going to tell you the index of the vector you're working with. When you do this colon here, it's going to do whatever your slice is on all of the vectors in your matrix. So all those columns get returned in the form of a new matrix, and all those columns will be sliced. That's what it's saying here. So for example here, we're going to go from the second index to the seventh index, not including the seventh index, and we're going to get all of those values for both of the vectors, for both of the columns, and that's what you're going to get here. Boom and bop. And when we call shape against this, of course, it's going to tell us that the shape now has turned from being 210 to 25. And then this example here, if you want to access all of the elements, not sure why you would do this, because you could just call the vector. But if you wanted to get all of the elements, another way to do it aside from just calling A would be to do colon, comma, colon. Just remember, when you do colon as one of these inputs for your slice, that colon just means all. Okay, it just means all the columns and all the rows, all of the elements and all of the vectors. And that's what you have here. So you can see how this here is the same as this here. Last thing is we want to access all the elements in one column. So let's say we want to pull something, but only like one of these vectors within our matrix. Then you can leave the second part of this tuple just as a colon, or you can just treat it like a vector and just call the index. Remember, the indexes of a matrix are the vectors, the indexes for the vectors contained in that matrix. So either one of these is fine. You know, there might be situations where doing it one way versus the other could be more beneficial. I would think like maybe parameterization might be a better case for doing it this way. Just remember that both of these are the same, I guess. So yes, this is just a quick review of these notes here. I'm going to publish these notes on LinkedIn, and just check down in the video description if you're watching this. You can get these. The best approach, honestly, is just to do this yourself, just to manually copy these exercises in. Oh, I got rid of time. That's where I used it. Just make sure you manually copy these exercises in yourself and make sense of them. This is really meant to be a guide, and so hopefully this will help you in your journey. The big thing is doing it yourself, though. These notes here, like I said, are coming from this Coursera course that is linked in the description. But this is like, just think about this as being 8 times more information than that Coursera course is going to provide for you. And it's always helpful to have like references like this for yourself in case you are working with something that you're rusty on. Putting things in your own words can be a lot more meaningful than just going and reading sterile impersonal documentation. So anyways, it's Friday, it's 6 o'clock. My Roomba is upside down because that's how I got it to stop making noise. So I'm gonna go tend to that. Thank you for coming to my little Friday night ratchet ghetto stream. You know what I'm saying? We're real rough and ragged over here, but we got it done. So thanks for being my study partner. This has really been great. I really appreciate pairing with you. You're so excellent, superb, sensational. So anyways, I'll catch you later. I never know how to end these things. I gotta come up with the outro or something. I'll think about it. Anyways, yeah, this has been OpenPair. This is the vectorization explanation. Check down below for the PDF version of this Deeplearning notebook, and I'll catch you next time where we'll be starting multiple linear regression. So, bye.